Okay, so today we'll be discussing the paper Neural Ordinary Differential Equations or Neural ODEs. This was a very novel paper from 2018, which also won the Best Paper Award in Europe's 2018. So what does it do? Okay, so they say they introduce a new family of neural network models, and instead of specifying a discrete sequence of hidden layers, we parameterize the derivative of the hidden state using a neural network. So what does that mean? Let's see here. So they say that uh, models such as a residual network, have a transformation which goes something like this. So what you usually have is that you have a hidden output, you have some input h, let's give it a time t, and you have some function f, which is a function of theta parameters, and you get ht plus 1 from it. This is, and this f could be a neural network. So this is a normal neural network. But in resonates, you have a skip connection like this, so that you add the input to the you add the input to the output of the network to get the output. So it is something actually like this. So this is ht plus 1. So ht plus 1 is the sum of passing this hidden state through this network and the input. So this is what a resonate is. So instead of predicting the output uh, independently, you predict the output as a residual or as a delta from what the you predict what should be added to this h of t to give h of t plus 1. You predict a residual, and this has been shown to work better. Now if you look at this equation, ht plus 1 equals to h of t plus f of h of t theta t. Let's write it something like equals to h of t plus t plus 1 minus t times f. So h of t plus 1 equals to this. Now this suddenly looks a bit, and let's make it even more obvious. H of t plus 1 minus h of t upon t plus 1 minus t equals to f. So now it should be glaringly obvious that in a way we can say that this f is actually a derivative. So we can actually say that this f is d of h by d of dt. Weird, right? That was my first reaction. Uh, so what this is that these iterative updates can be seen as a Euler discretization of a continuous transformation. Euler discretization is nothing but what I sort of alluded to here. It is something like x of t plus delta t equals x of t plus delta t times uh, dx by dt. This is what a Euler uh, update or a Euler but this is what a Euler update looks like. So if you have a function like this and you're at a time step t, you predict and say this is the gradient here. It totally does not look like the gradient here, but let's just say that is the gradient here. You say that the value at t plus delta would be t plus delta t would be delta t times the slope. So this is what you call a Euler update. And they say that resonates are sort of like a discrete version of this. But if you take the limit, if you make this delta t smaller and smaller and smaller, you actually get a continuous update. And in that limit, you can actually represent the thing as something like this: dh by dt equals to f of h of t comma theta. So if you, so in this case, the delta t was 1. If you represent it for a generic delta t, this might be what it looks like. Let's just write f here. And in the case that delta t goes to 0, f becomes the derivative. So this is what it is. So what they tried, what the point they're making is that uh, you can actually, for resonance, you can see resonance as a discrete version of something more general, where you are actually learning the derivative of how a hidden state changes. So instead of modeling uh, H directly, you don't model H, you model dH by dt. You instead predict this using your neural network. So say you want to learn a function y, instead of directly learning x, a function which goes from x to y, you instead learn a function f which is equal to dy by d of x. So you learn the derivative instead. And once you have the derivative, you can actually predict the y using Euler update, which looks something like this. So if you want to predict a y, then you can actually like just uh, you need a starting point. You need some y naught, and then you can be like y equals to y naught plus delta x times dy by dx, something like that. So yeah, so that is what we can see here also, that starting from the input h of 0, so at t equal to 0, we can define the output layer to be a solution to this ODE problem at some time t. This value can be computed by black box differential equation solvers, which evaluates the hidden unit dynamics wherever necessary to determine the solution with desired accuracy. What it basically means is that if you take this and integrate it, it would be something like h at time t equals h at 0 plus integral of dh by dt, which is nothing but f, so f dt, t equal to 0 from to t equal to t. So this is what you do. So while you can't calculate this integral, there are numerical methods to solve this, such as the Euler method, in which you just discretize this and update it. So h of t plus 1 becomes h of t plus delta t times f at t. So you start at some input layer 0 and you just use this update again and again to get the final value, which is actually your output. And in this case, you have to uh, do a pass through f at every evaluation point. So this is what they represented visually. Key A residual network defines a discrete set of fine transitions. So this is the depth. So this means like you have around 5 residual layers stacked on top of each other, and so one means that you pass the input through one ResNet. Second means you pass it to another residual layer. Third means another residual layer. Fourth, another residual. So you totally pass it to 5 residual layers, and this is how the input changes. So you are just doing 5 discrete uh, applications. In OD, instead you have a continuous thing. You don't have any discretized thing. So your depth is continuous. There is no concept of a layer as such. You just have a single thing, and uh, each input is continuously mapped to different outputs at different level of depth. So you get a sort of a vector field, and you can evaluate it. You can, starting from here, you can get it at any point by having being at the start point and knowing the delta t. You can take the value here, you can take the gradient at this point and evaluate this at any point you want, not just at these discrete intervals, but any point in between. So yeah, it is sort of like, instead of having a discrete depth, you have a continuous depth in this case. And why is this useful? So the main advantage, one of the main advantage of these networks is that they are memory efficient. So they say that in a later section, which we'll cover later as well, they show how to compute gradients with respect to the inputs without backpropagating to the operations of the solver. Not storing any intermediate quantities of the forward pass allows us to train models with constant memory as a function of depth. So what they mean is, let's see. Okay, well, I don't need a sparkle. Let's just change this color to red. And yeah. So let's say this is T and this is H. We start at 0 at some value H naught, and so this is our input, and we use the Euler method or whatever method to get the evaluation at some time H of, at some time T, uh, discretizing the process at a few steps. So we are at H naught, we calculate the gradient here, and we take a step, then we calculate the gradient here, then we take a step, then we calculate a gradient here, take a step, take a step, take a step, calculate, take a step, calculate, take a step. In the end, after a few steps, we'll reach T and we'll get the H of T. This T is the quote unquote uh, depth, and this is the hidden layer, which is the output, hidden state, which is the output. So this is that. So this is in a way the forward pass. Now we want to, and we have a loss function and we'll calculate the loss here. Now we want to calculate the gradients of the loss with respect to the hidden state at this particular point. We can do two things. Actually, let us just first thing of the most obvious way. Because our neural network is supposedly differentiable, all these forward steps would be differentiable. So we can just use backpropagation to backpropagate through time and get the gradients. This could be done, but this would require us storing the forward values at each of these intermediate steps. Because if you want to calculate the gradient using autodiff or something, we'll need to store the values of the forward pass. And this would make it O of L in memory. One of the main innovations of this paper is that via some trick, which we'll discuss later, you can start at a point, at this point T, and sort of run a reverse process, a reverse ODE process, and calculate the gradient here. So you don't need to store all these values during the forward pass. You start at the final result and you run this another process backward using a similar approach as the forward one. So you don't have to store the values which you got in the forward pass. You will create a new set of values in the backward pass and get the output. So this would be O of 1 in memory, not O of L. You might be thinking that we still need L, these L values, but no, actually to calculate the value here, you just need the previous one, right? You don't need to store all of them. So this is O of 1 in memory. It is still O of L in computation. You can't directly calculate the gradient here. You have to like break it down into chunks and calculate it, but it is still very, very memory efficient. So yeah, overfill memory, overfill time. Another thing is that of adaptive computation. So they say that Euler methods is one of the simplest method for solving ODEs, and there are more complex ways of doing this. ODE, by the way, is just this equation, this equation, and solving it means solving this integral, which you can do using multiple approaches. One of them is the Euler method. They say that there are multiple other ways to do this, and some of them even have adaptive computation. So they say that modern ODE solvers provide guarantees about the growth of approximation error, monitor the level of error, and adapt their strategy on the fly to achieve the requested level of accuracy. This allows the cost of evaluating a model to scale with problem complexity. After training, accuracy can be reduced to real-time power applications. So what they mean is that solving this integral can be done by multiple ways, by multiple solvers, and there are some solvers which can adaptively. This is what takes the computation. So even in Euler's method, this is where you have to do the forward passes again and again. So there are other solvers which uh, adapt their computation regarding based on how complex the input is. So you can use any solver here. It is independent of your design. So you can use any solver there. You can train using one solver which is complex, and you can uh, test using another solver during inference time, which is much simpler. So you have a way of like changing the competition as you suit. So which is very good. Normalizing, they have a bunch of things on normalizing flows, which I'll be skipping because I don't understand normalizing flows. I don't think nobody even really uses them right now. Also, they say that uh, their models with the continuous with a continuous nature can naturally incorporate data which arrives at arbitrary types. So because T is continuous and not discrete, they can handle data which occurs at irregular time periods, which does not occur at like 0, 1, 2, 3, 4, 5, which might occur at like 0, 0.5, 1, 1.3, 2, 2.5 irregular periods, because it is their formulation is continuous, so they don't necessarily need it to be evenly spaced. So yeah, these are the advantages. So let's see, how do we do the backpropagation in this process, or how do we calculate the gradients in O1 memory instead of doing backpropagation through time. So the method they use is supposedly a very common method. It is called adjoint sensitivity. And in this case, you calculate the gradients by solving a second augmented ODE backwards in time, and it is applicable to all ODE solvers. So now they somehow suddenly changed H to Z. Z is the same as H, don't get confused. So if we start at some time T naught and we use the forward ODE solver, we use this integral or whatever. Well, we are trying to calculate this integral, but since we can't calculate it, we use some sort of ODE solver to calculate it. One of this is our Euler method, and we get this final Z. To optimize, and we calculate the loss at this state. Now to optimize L, we require gradients with respect to the parameters theta to theta. So we don't have them. We have to figure out a way to find them. So the first step is to determine how the gradient depends on the hidden state zt at each instant. So what they say is that the first step is to model something called the adjoint, which is del of L by del of Z at time t. Right. This is something which they say we have to calculate. And they say that its dynamics are given by another ODE, which is this. How this is derived is given in the appendix. You can look at it if you want. But essentially, this is how this is a of t, and this is how the gradient of a of t is determined. So dA by dt equals to minus A transpose d of f by d of z, right? So we know A t because at any point L, we know the value at, we know this value at the final time step Tn because we know the z at that point, and we can calculate the loss there, so we can calculate what the gradient is there, and we also can evaluate uh, this gradient because this is just the gradient you obtain by passing z of t through the function. So all of this is known to us. So we know the value at this end step, and uh, so to evaluate this, we actually just need to know the z at that point. To evaluate this at any point in time, we need to know the z at that time. So we can just run this process backward in time, solve this ODE backward, uh, and get the value of this A at the initial time step. So you run this ODE backward in time to get the value of A uh, at the initial time step. So that is how you get the uh, value of A at different time steps. And they said that in the end, since you want the value of theta, theta is also given by another OD, which depends on both Z and A, and is given by this. All right. So in essence, you also you go through the entire process and you figure out, you run another OD to get this value of this gradient at the initial time step. Right. So in essence, TLDR, you had this diagram. Where did that diagram go away? Yeah, you had this diagram, and in the forward pass, you started at a time step and you got the value at this time step. To calculate the gradients, you need some other quantities at the, the end, and you need to calculate the gradients at the beginning. So these gradients are sort of given by another ODE, which you just solve backward in time to calculate the value of the gradients in the beginning. And it involves a bunch of maths, which you can look into it if you want to. So another cool thing is that instead of solving these three ODs for Z, A, and theta, uh, you can actually solve all the ODs in a single step using a single OD, and this basically involves combining all of these three parameters into all of these three variables Z, A, and del L by del theta. Oh wait, in the third OD we were actually modeling the gradient only itself, not that is what we would be modeling. So yeah, you create an augmented state which has all these three, and you create a single OD for it. So this is how it is. You have input. So this is the reverse mode. This is how you do backprop here. So you have theta as input, the start time t0, t1, the final state zt, and the loss gradient at the final time step. So you have all the values at the final time step, and you have to figure it out at the initial time step. So this augmented state, you create this augmented state, which is given by z del L by del z and 0. Del L by del z is nothing but A of t1. So, and these are the parameters at theta t. So this is what you get. These are the derivatives of this quantity. So this function determines the derivative of z is f of z, derivative of a of d is this, and derivative of theta is given by this thing. This is this. 0 is actually del of theta by del of t is what I think it is, probably. Or actually it is del of L by del of theta at time t. And this is its gradient. Basically, this is this. If you call this to be g, then this is d of g by d of whatever, d of t. So yeah, this is actually d of, this is actually g at time t. Anyway, in short, you create this augmented state, and once you have the initial state and the derivatives of that state, you can run this ODE solver to run this backward in time and get its value at any time step, and that also involves time step t equal to 0. And in the end, what you're concerned about is this final value, del L by del theta at t equal to 0. Right, so this is how you do a backward pass for neural ODs. So that is mostly it for how you train these methods. We covered the forward pass and the backward pass. Now it is mostly experimentation. So first they tried replacing residual networks with ODs for supervised learning on MNIST, and they observed that they get similar accuracy as a ResNet while having very less memory. Second is the error control. So they say that ODs can approximately ensure that output is within a given tolerance of the true solution, and changing this tolerance changes the behavior of the network. So first they verify that this error can indeed be controlled. So NFE forward is the number of forward function evaluations you do, and so it is sort of an indicator of how much computation the OD solver used, and they see if that they increase the number of computation, then they can drive the numerical error down. This numerical error is not the actual error. I think this is the error in approximating the values using a OD solver. So in an OD solver, you are approximating this using a gradient, and you reach somewhere which might not be the actual value you want to reach. And I think that this is the error they're talking about, not necessarily the classification error or something. Probably, I don't know. So, but anyway, the numerical error can be controlled with the number of forward time steps. Uh, the time spent by a forward call is proportional to the number of function evaluations, which makes sense. I mean, the more number of evaluations, the more time you would take. Uh, the number of evaluations in the backward pass is roughly half of the forward pass. So why do we need evaluations in the so if we do a forward pass, why do we need evaluations in the backward pass? That is just to do the adjoint method where we calculate where we use a backward ODE. So the evaluations there are supposedly half than that of the forward pass, which is good because it makes it much more feasible. It is already feasible from a memory point of view. Even from a computation point of view, it seems nice. Uh, Finally, they investigate the network depth. So it is not clear how to define the depth of an ODE solution. A related quantity is the number of evaluations required of the hidden states. Uh, that is, which is a detail delegated to the ODE solver and dependent on the initial state. So this ODE solver, which approximates this integral, this can discretize this as it requires, and each discretization would require a forward pass or a network evaluation. And in modern ODE solvers, that depends on the complexity. And what they observe is that as the tuning progresses, the number of evaluations increases. And this is presumably to adapt to the increasing complexity of the model, because the model is learning more and more. It is becoming more and more complex. It has to do more evaluations to approximate that complexity. So yeah, this is a cool bunch of experiments. I'll skip normalizing flows experiment because I don't understand them at all. uh, Another experiment they do is the generative latent function time series model, which is basically modeling time series data sampled at irregular time steps. So this says that applying neural networks to irregularly sampled data is difficult. Typically, observations are put into bunches of fixed duration, which is not good, because if they are at uneven time steps, you need some way to model that unevenness, because that might have some information. And sometimes this is addressed by concatenating timestamp to the input, but they need a better way to handle this. And since they say that since ODEs deal with continuous time, it is very natural to use them to model this approach. They use a VAE formulation for this. I think it is best explained to this one. So what they do is that you have these n observations. You pass them through an RNN, and these observations might be at different time steps. You don't really care. You pass them through an RNN, and you get this hidden state. Then you use this hidden state to infer a initial latent z of t of 0. So this initial latent encodes the entire history. And then you just run this OD solver to get the latents z of t1, z of t2, z of t3 at whatever time step you require. These t1, t2, t3 don't need to be regularly sampled. They can be sampled at any point. So yeah, that is the cool thing about it. You can do this at any point. You can extrapolate how much you want. So you can train it by predicting it for the same values, and you can do extrapolation as well. You can do whatever you want. And because it is continuous, it will be able to handle irregularly sampled data points as well. They do it in a VAE fashion. I think that detail is not that important. The detail which is important is that because it can deal with continuous time, you can apply this to irregularly sampled intervals as well. So yeah, here they try to here they show the superiority of their approach in time series modeling, I think. So they are trying to approximate this spiral, and they have data only for this, and this red part is something that the model has to learn to extrapolate itself. As you can see, it sort of fails in this region, whereas their model is able to learn this in a better way. Also, they say that uh, if they vary the latents of their learned latent, if they vary the dimensions of the latent, they can make the spiral turn clockwise or anti-clockwise. So their latent has learned some sense of directionality in it as well. Uh, and also it has a better MSE than an RN. So it is better than using an RN for irregularly sampled data. So what are some limitations of the paper? One of them is batching. So it is not very clear how to batch these systems, because you have to pass them through an ODE solver, and it is not very clear how to batch multiple inputs through an ODE solver without increasing the competition. You can like put everything in the state and do it, but it is some competition complexity and uniqueness. This is some We are assuming a lot of mathematical things when we are saying that this can be solved through this ODE can be solved through through an ODE solver and something. So all those mathematical guarantees should be there. Setting tolerances. So when using an ODE solver, you specify a tolerance of the error you would accept between the value it is supposed to predict and the value it is predicting. So you have to set these tolerances, and this is an additional hyperparameter. And the model would be sensitive to these tolerances as seen as in that previous experiment, where changing the tolerance changes the amount of computation the model does. So that is another thing. That is an additional hyperparameter. Then there are numerical errors which can occur. So this especially occurs in the adjoint calculation because uh, if you start from this point and go from this point and you calculate the reverse process, it is not always guaranteed that you would reach here. If there are some numerical errors, you might reach some other weird point while going back. So yeah, it is hard to reconstruct forward trajectories while only at the end. And I was seeing a talk on liquid neural networks, liquid time constant neural networks, and exactly because of this method, they sometimes just prefer using backpropagation to time. So not using the set joint method, but just using the backpropagation through time in the forward pass only to calculate the gradients, which is more computation, which is more expensive from a memory point of view, but is much more accurate and stable. So yeah, that was mostly for the paper. Overall, I think it was a very cool paper. It has a lot of follow-up works. It was a very novel idea. I'm not very sure how. This was in 2019. We are in 2023, 2018 or 2019. I don't know. But we are in 2023, and not many people talk about neural ODEs. There are some works here and there. You can say that diffusion models are in a way sort of neural ODEs. In that sense, they are still going strong. But yeah, given the promises, I expected a lot of work to be done. There is some work definitely, but not as much as I would expect, which is weird. But yeah, overall, it was a very cool paper. Do check out their original code. Do check out the follow-up works. Deep equilibrium models is one which comes to my mind. There is augmented ODs and many other liquid neural networks. All this other cool stuff. Do check them out. I'll link some blogs in the description which helped me understand this paper better. And yeah, that's all for the video. Thanks for watching.